Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Environmental Degradation of Materials due to High Temperature of Oxidation Part 2 from the paper Functional Materials. The purpose of this module is to make the students familiar with first, the fundamentals of high temperature oxidation of metals, second, the thermodynamics and kinetics of oxidation. So students, let us start with a basic introduction about the module. In this module, we shall look at a very important degradation phenomenon that occurs in materials, especially those exposed to higher temperatures in service. We shall primarily focus attention on high temperature oxidation of metals. The same principles can be used to understand the high temperature degradation phenomenon in ceramics and composites. However, the high temperature degradation is important in no oxide ceramics like carbides, nitrides, suicides, and etc. One typical example is heat-resistant coating on the nose of space re-entry vehicles. So let us take a brief look at the sequence of events that normally take place when a material is exposed to higher temperatures. So oxygen first adsorbs on the surface before disassociating on the surface to the monoatomic form. So when free energy considerations favor the oxide formation, this oxide will nucleate on the surface and grow laterally, covering the whole surface. At the same time, oxygen may also dissolve in the parent material, like in the case of metals like titanium, palladium, platinum, and copper. Once the oxide growth takes place by the diffusion of ions and charges in oxides, the dissolved oxygen may penetrate into the metal and leading to the formation of the oxide, and this process is known as internal oxidation. Several kinds of defects can develop in the growing oxide scale. These include porosities, cavities, and microcracks. With increasing oxide thickness, macrocracks may appear. Macrocracks allow the environment to directly react with the metal at the metal oxide interface. Other processes like molten phase formation, oxide evaporation, and liquid metal oxide formation may also occur depending on the environmental conditions and the material system. Oxygen oxide induced embrititlement of matrix materials is also known to occur in some systems. Oxidation reactions. Oxidation
reactions are primarily caused by oxygen. Oxidation can also be caused by moisture and carbon dioxide. These situations are indicated by the following equations, that is xm plus half yo is equal to mx/oy. xm plus yH2O gives mx/oy plus yH2. xm plus yCO2 gives us mx/oy plus yCO. Recollect that oxidation is electrochemical in nature. To recollect the important points, the four components of the electrochemical cell are the metal-metal oxide interface anode, metal oxide environment interface cathode, and the oxide which acts as the electrolyte as well as the electronic conductor. The process of oxide layer formation is a combination of two half-cell chemical reactions, that is, M plus 0.5 O2 gives us MO oxidation. Cathodic reaction is M minus 2 electrons gives us M2 plus, and anodic reaction is O plus 2 electrons gives us O2 minus.
Now students, let us discuss the thermodynamics of oxidation. The equation is given by delta G degree equal to delta H degree minus T delta S degree, and the plots between delta G degree and the temperature, they are known as Ellingham diagrams. The intercept of the line at T is equal to 0 Kelvin, it will be equal to delta H degree. The slope of the line will be almost constant because all oxidation reactions involves the disappearance of 1 mole of oxygen gas, and it is also equal to minus delta S. There will be a change in the slope at temperatures where phase transformations occur, like for example melting of metal oxide or the vaporization of metal oxide. This diagram provides a quick way to determine the relative stabilities of various oxides.
Ellingham diagram. Unlike the concept of equilibrium dissociation pressure, we can construct a nomographic scale on the right bottom of the Ellingham diagram to directly obtain the dissociation partial pressure of an oxide at any temperature. We connect the point O provided on the y-axis where temperature is 0 Kelvin to the plot at the temperature of interest and extrapolate to the monograph. It can be noticed that the oxygen partial pressure is attained depending on H2O H2 and CO2 CO can be plotted on the Ellingham diagram. Oxidation structure. When we discussed the electrochemical nature of oxidation, we had noted that the oxidation or the oxide act as the electrolyte through which the ions diffuse. So now we shall get little more specific. In that example, we had assumed that the metal ion species were the dominating diffusing species in this oxide. So now let us consider the case of stoichiometric oxide, where the major defects are Schottky and Frenkel defects. So defects can be classed as those that form in stoichiometric oxides and those in non-stoichiometric oxides. A Schottky defect is defined as a missing pair of cation and anion as shown in this figure. In oxides with Schottky defects, diffusion can take place through both the cation and the anion sites. A Frenkel defect is defined as when a missing cation at the regular site occupies an interstitial site. Non-stoichiometric oxides can be classified as N-type or P-type oxides depending on the electronic conductivity of the oxides. Now, in the case of N-type oxides, there are excess of metal ions or the deficiency of oxygen ions. The typical example is zinc oxide, where the excess zinc ions are located in the interstitial sites and the electrons contributed by the excess interstitial ions make the oxide as the N-type conductor. Whereas in the case of P-type oxides, the main charge carriers are holes. Holes can be defined as the locations where electrons are missing. And the typical example of P-type oxide is the wurtzite iron oxide. Notice that since the metal ions are not in the stoichiometric ratio and the charge balance has to be maintained, so the extra electrons needed to ionize the oxygen ions are provided by iron going to a higher valence state. Therefore, the structure of the oxide will consist of vacancies on the metal cation sites and the holes at the location of ferric ions. Oxidation kinetics. Although a metal may possess the necessary tendency to oxidize, it is the rate of oxidation that will ultimately determine whether the degradation is harmful or not. So, if the rate is small, then oxidation rate can be manageable, can be taken into account while designing the product. In case if the oxidation is excessive, then there are problems that have to be tackled. We have just learned above that the oxidation rate will be high or will be low depending on the defect structure of the oxide. Now let us look at how the oxidation rates can be understood and analyzed in a systematic manner. In order to determine the oxidation kinetics, it is important to obtain the kinetic data in the form of weight changes or as a function of time at the temperature of interest, that is isothermal. While the data can be collected using the individual samples at the same temperature, the usefulness of the continuous weight gain measurements are considerable. It will help to detect the onset of other processes like oscillation and the oxide spallation, that is detachment of the oxide from the surface and falling off, oxide cracking, etc. Once the weight change data is collected as a function of time, it can be analyzed. Now continuing our discussion on the oxide kinetics, there are various laws governing the oxide kinetics. First law which we will be discussing is the parabolic rate law. This is the most popular oxide growth law that is used to analyze mostly the weight gain data. The parabolic rate law can be derived rigorously, and mathematically it can be expressed as x square equal to kp multiplied by t, where x is the thickness of oxide layer, t is the time, and kp is the parabolic rate constant. The parabolic rate law can be derived by considering the diffusion controlled growth of the oxide film. This figure shows the steady state flux of diffusion of metal ions from the metal oxide interface to the oxide environment interface is rate controlling. The next law which we are going to study is the linear rate law. The linear rate law is given by x is equal to k1 multiplied by t, where x is the thickness of the oxide, t is the time, and k1 is the linear oxidation rate constant. Linear oxidation kinetics in continuous increases in oxide thickness with time, and this is the indicative of non-protective nature of the oxide formed. The non-protectiveness of scales can be due to several different reasons. One is the fact that the volume of the oxide formed from the metal is lower than the volume of the metal from which it is formed. The oxide thus formed will not cover the surface and lead to non-covering, non-protective oxide scale. There can be other reasons for non-protectiveness like micro-cracking of the scale or spallation of the oxide scale. The next type of law is the logarithmic rate law. The logarithmic rate law is expressed as x is equal to k1 multiplied by log of at plus b, where k1 is the logarithmic rate constant and a and b are the constants. This law is generally noticed for thin film oxidation, like in the case of oxidation at lower temperatures. Next type of law which we are going to see is the Pilling-Bedworth ratio. The effectiveness of the coverage of the surface of the oxide is given by Pilling-Bedworth ratio, which is the ratio of the volume of the metal oxide to the volume of the metal from which it is formed. One can derive the mathematical relationship for this once the density of the oxide and the metal are known, as well as the number for the metal atoms in one formula unit of the oxide. So when the ratio is less than 1, then we have non-protective oxide, and when it is too much greater than 1, then we again have non-protective oxide due to oxide spallation due to a large compressive stress developed in the oxide. Ideally, the best protective oxide have PBR in the range of 1 to 1.5.
Effect of alloying on oxidation. Let us consider a case of N-type oxide, for example, zinc oxide. So we'll consider two cases. First case is the introduction of lower valence metallic ions in the oxide. So in this case, the concentration of interstitial metallic ion increases and the number of excess electrons they are decreased. A diffusion controlled oxidation rate increases. Now consider the second case, the introduction of higher valence metallic ion in the oxide. In this case, the concentration of interstitial metallic ion decreases and the number of excess electrons increases. So a diffusion controlled oxidation rate overall decreases.
Effect of alloying on oxidation. So students, let us now consider the case of p-type oxide, for example, nickel oxide. So introduction of lower valence metallic ion in the oxide, that is the concentration of cation vacancy decreases and number of electron holes increases, indicating a diffusion controlled oxidation rate decreases. Next is the introduction of higher valence metallic ion in the oxide. Now here the concentration of cation vacancy increases and number of electron holes decreases, that is indicating a diffusion controlled oxidation rate increases. Hot corrosion. Hot corrosion does not mean the corrosion at higher temperature, but it refers to a form of high temperature degradation wherein the surface oxides are converted to non-protective scales due to the reaction with species in the environment or based on the chemistry of the material. Let us take a typical example. In the case of jet engines, air is injected and then compressed, mixed with the fuel and ignited. The gas produced is at the temperature between 700 to 1400 degrees Celsius. Part of the gas is used for providing thrust to the airframe and the rest for running a turbine that supplies power to the aircraft. When jet engines operate in marine environment, which is frequent in a country like India with a large coastline, then problems arises due to NaCl that comes in through the ingested air. Hot corrosion is a combination of oxidation and reaction with sulfur, vanadium, sodium, and chlorine, leading to non-protective scale formation. The NaCl that is ingested into the engine reacts with sulfur from the fuel to form Na2SO4 as per the following reaction. 2NaCl plus S plus 3 by 2 O2 plus H2O gives Na2SO4 plus 2HCl. NaCl and Na2SO4 from a low melting eutectic on the surface. Melting point is about 620 degrees Celsius. Na2SO4 can be thought to consist of acid and base components are per Na2SO4 gives Na2O plus SO3. The metal oxide can be fluxed by either the acid component SO3 forming the metal ions as per MO plus SO3 gives us M2 plus SO4 2 minus, or with the base component Na2O forming anions as per MO plus Na2O gives MO 2 minus plus 2 Na plus. In either case, the protective MO scale is removed, and this leads to the enhanced rate of attack.
So students, let us summarize what we have learnt in this module. First, the oxidation reaction leading to material degradation caused by moisture and carbon dioxide along with the relevant equations was discussed. Second, the thermodynamics of oxidation along with Ellingham diagram was discussed in detail. Third, the oxidation kinetics along with the 4 laws governing the kinetics of oxidation were discussed in detail. The the next thing which we discussed is the effect of alloying on the oxidation of N-type and P-type metal oxides. Lastly, the concept of hot corrosion was also explained. Thank you.